All right, 4.6 is matrices and transformations. I promise today is going to be easier than the past two lessons. Okay, so we're going to start off with our objectives. We're going to write a matrix equation for the transformation of a figure, and we're going to graph both the image and the pre-image of a transformation on the same coordinate plane as we're going through here. All right, so let's recall. A transformation is a change made to a figure. The pre-image is the original figure. The image is the figure produced by the transformation. And so it would sometimes make more sense if it was like image and post-image, but it's not. Pre-image is your original. Image is after the transformation. Okay, so transformations include translations, reflections, rotations, and dilations. But these three, right, the translation, the reflection, the rotation, are going to produce congruent images. The dilation does not. Okay, so your translation is a figure that slides without any rotating, resizing, or reshaping. Okay, so they're just sliding an image left or right, up or down, or a combination of those. Okay. Okay, a reflection then is, I was looking for this table. Okay, a reflection is a figure is reflected across a reference line, such as your X or Y axis. So here, this is my reference line. I reflected it from here over to here. A rotation, a figure is rotated around a reference point. Okay, so let's go back. A reflection is a reference line. In a rotation, we have a reference point, okay, which is commonly the origin, but not always. And the last one, the dilation. That's when a figure is enlarged or reduced, producing a similar image. This is the only one that is similar. The rest are all congruent. Okay, so this one is similar. So notice this one here is your original. That's your pre-image. And it's, or no, I have, yeah. And then this is your image. That's the post one. We have enlarged it there. Okay, so there's different rules that apply to each of these. Different formulas and everything else in the matrix. And these, okay, the other thing to know about these is like graphic design, traditional art, like these students are often amazed, okay, at the amount of mathematics used in art. Artists and designers are going to employ, are going to use ratios, angles, scaling, translations, dimensions, all of those things that are creating digital images, and they're generated and manipulated mathematically. Matrices are also used to rotate 3D computer graphics and all kinds of things. So if you are tech savvy and things, like matrices are very helpful for you. All right, so first up, we have the translations. Okay, so the matrix equation at right can be used to translate triangle XYZ 3 units left and up 1 unit. So 3 units left is a negative 3, right? That's how we notate that. And 1 unit up is a positive 1. Okay, so it's plus 1 because we're moving up, minus 3 because we're moving left. Okay, so in this case, two to note, pre-image is named X, the image is named X prime. All right, or here they have F and F prime. Either way. All right, but T is our translation matrix. So notice, okay, so we have our X, Y, and our Z points, X, Y, and Z points. This is our X coordinate and our Y coordinate. So for X, it's at 1, 1. Okay, so that's where this point came from. Y is at 4, right? It's here. It's at 4, 4. And then Z, okay, so that's why here we have 4, 4. And Z is at 4, 2. So over 4, up 2. So that's where these coordinates come from. So we are adding a negative 3, because we're moving it every piece left 3, and positive 1, because we're moving each point up 1. If you remember, hopefully, how to add matrices, you just add the corresponding parts. So negative 1 plus negative 3 is negative 2. 4 plus negative 3 is 1. 4 plus negative 3 is 1. 1 plus 1 is 2. 4 plus 1 is 5. 2 plus 1 is that, yeah, 2 plus 1 is 3. So now these are our new coordinates. So we have -2, 2. So -2, 2 for x prime. 1, 5. So 1, 5 for y prime. And 1, 3. So 1, 3 for z prime. Is this the same as like, okay, I started here, I'm going to go left 3, 1, 2, 3, and up 1. Bam! Yes, it's the same thing as doing that. So you could check it that way, but we're actually going to work on the matrices part here. Okay, so write a matrix equation, example 1. Write a matrix equation translating triangle ABC 4 units right, so that's going to be plus 4, and 5 units down. Okay, that's going to be minus 5. Then graph the pre-image and the image on the same coordinate plane. Okay, so let's start with, we need our A, B, and our C. Okay, so A here is -4, 3. So -4, 3. B is -1, 2. -1, 2. And C is -2, 1. Okay, so that's our pre-image. We're going to add, so it needs to be 3 columns, right? 2 rows, so a 2 by 3, same size. And our right and left are x coordinates, so that's going to go up here. So we're going to add 4. So 4, 4, 4. We're going to go down 5, so it's going to be -5, and -5, -5. And so our solution matrix here, -4 plus 4 is 0. -1 plus 4 is 3. -2 plus 4 is 2. 3 minus 5 is -2. 2 minus 5 is -3. And 1 minus 5 is -4. Okay, so we want to graph these on the same one, it said too, so we can do that. So let's graph our original. I'm going to do it in purple. So I've got -4, 1, 2, 3, 4, 1, 2, 3. So that's A. -1, 2, -1, 1, 2 is B. And -2, 1, 2, 1 is C. All right, then let's do our second one. So we have 0, -2. So 0, -2. That's my A prime. 3, -3. 1, 2, 3. 1, 2, 3. That's my B prime. And 2, -4. 1, 2, 1, 2, 3, 4. That's my C prime. There we go. That's, I mean, it's really simple math and things. It's just knowing how to use them. Okay, let's look at the reflections then. Lots of things there. All right, so reflections. A reflection is a transformation across a reference line, remember it was a reference line, that creates a mirror image that is symmetric with that line. So there was also creating a line of symmetry. So left multiplying, matrix F, which is a 2 by n, a matrix representing the vertices of a figure, by the following matrices will produce each stated reflection. And I get that this makes no sense, utterly no sense, but we're going to make it make sense. So if we look at this table for reflections, we have R, reflection, across the y-axis. Okay, that's what it says, across the y-axis. It is going to be -1, 0, 0, 1. So our x, y coordinates are going to actually change to -x, +y. That's the easier way to think about it. But we're going to use the matrices part. If we do a reflection across the x-axis, we're going to use this matrix. A reflection on the y equals x axis, okay, we're going to use this matrix. And if we're doing a reflection across the y equals negative x line, we're going to use this matrix. Okay, which again, I know we're going to have to flip back and forth maybe a little bit for example 2, but we're going to make it make sense. And so let me clear this a little bit. All right, so for example 2, write a matrix equation reflecting triangle TUV across each line. Then graph the pre-image and the image on the same coordinate plane. Okay, so first of all, let's look at TUV. Let's get these points here first. So T is 2, 1. So we have them. U is 5, 3. And V is 5, 1. Okay, so we have those. So left multiplying, if I go back to this idea, okay, it says we're going to left multiplying. That's what we had to do yesterday in our notes, okay? When we did, right, we had AX equals C and we multiplied by the inverse. We had X equals the inverse of A times C. It's called left multiplying because we have to put the matrix that we're multiplying by on the left side of the matrix we currently have. Okay, so we have to left multiply. That's what that means, since I didn't explain that before. So on problem 1, A is we're reflecting it on the Y, across the y-axis. So we're going to use this one this matrix right here, the negative 1, 0, 0, 1. Okay, that's how we're going to solve this first one. Okay, and we have to left multiply. Okay, so we're going to take that matrix and put it on the left. So we're going to have negative 1, 0, 0, 1. And we're going to multiply it by the matrix, like these numbers in a matrix. So let's do TUV in that order. So we're going to have 2, 1, 5, 3, and 5, 1. Okay, it's always good to check. I'm multiplying a 2 by 2 times a 2 by 3. Yes, I can multiply because I have 2's on the inside, and my solution is going to be a 2 by 3. Okay, so that's always helpful to remember. Okay, so this is going to equal negative 1 times 2 plus 0 times 1. I don't usually write it like that. Man, I'm going to take up a lot of space if I write it all out. We may skip it. Let's see. See if we can hold on to the numbers. So negative 1 times 2 is 2. 0 times 1 is 0. So 2 plus 0. I might just do it that way. Okay, then we have negative 1 times 5 is negative 5. And this one should have been a negative 2. I didn't write the negative. 0 times 3 is 0. Each of those is going to be 0, but that's okay. Negative 1 times 5 is negative 5. 0 times 1 is 0. Okay, so there's our first row. Now for our next one. 0 times 2 is 0. 1 times 1 is 1. So this is 0 plus 1. 0 times 5 is 0. 1 times 3 is 3. 0 times 5 is 0. 1 times 1 is 1. Okay, so our new points are going to be negative 2, negative 5, negative 5, 1, 3, 1. Okay, so that is our image. Okay, so if we graph these, actually, so I've got 2, 1. I'm just going to graph this one. 5, 3, 5, 1. Okay, I'm not labeling them. You should. I just don't want to take forever again on your notes tonight, so I'm sorry. Let's graph. So this is our pre-image. Let's graph our image. So we've got -2, 1, -5, 3, and -5, 1. So remember, it was across the y-axis. So is this, like one way you can say, like, is this a line of symmetry? Well, yeah, this point is 2 away from the axis, and this one's also 2 away. Or if we go up here, this one's 5 away, this one's 5 away to the left. So we have that line of symmetry. All right, good work. On B, this time we're doing the y equals x axis. So that requires a different matrix to start with, that we left multiply a different matrix. Okay, so this time we're going to left multiply by 0, 1, 1, 0. Okay, because that's the y equals x on the reflection chart. Okay, we're going to multiply that by our matrix of points, of coordinates. So 2, 5, 5, 1, 3, 1. All right, and we were able to keep track of it earlier. So let's see if we can do that again. So 0 times 2 is just going to be 0. 1 times 1 is 1. 0 times 5 is 0. 1 times 3 is 3. 0 times 5 is 0. 1 times 1 is 1. Okay, and then let's move to the next one. 1 times 2 is 2. 0 times 1 is 0. So this is going to be a 2. 1 times 5 is 5. 0 times 3 is 0. So it stays 5. 1 times 5 is 5. 0 times 1 is 0. So this is 5. All right, so if I graph my pre-image, again, I have 2, 1, 5, 1, 5, 1, 2, 3. Okay, here's my pre-image. And my image is 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, and 1, 5. 1, 2, 3, 4, 5. Okay, and if I look at that line of symmetry, it's the y equals x. So when y is 1, x is 1. When y is 2, x is 2. So I've got a line of symmetry that's a diagonal across there. And yeah, that is symmetrical to that. Okay, so great job with this reflection one. All right, next up is the rotations. Okay, so again, with rotations, we're going to do left multiply. Okay, so we're going to left multiply this, an F2 by N matrix, so one of these. Or any one that we have, it's a 2 by N, because we have an X value and a Y value, right? So it's saying I have 2, an X and a Y by however many we need. Okay, can also produce transformations where the image is rotated or spun about the origin. Okay, we will only consider counterclockwise rotations in this book and in this text. Okay, so when we have those, okay, we are going to have different matrices again depending on what's happening, but they're all counterclockwise rotations. So 90 degrees counterclockwise, 180 degrees, 270, or 360. Okay, that we're going to do. And these are ways to check down here. You might have seen us use during algebra, remembering these. But the matrices are the things that do the math to get us there. All right, so example 3, we're going to write a matrix equation, rotating triangle DEF, 90 degrees, counterclockwise, around the origin. Then we're going to graph the pre-image and the image on the same coordinate plane. Okay, so let's look at DEF and go ahead and get our points for DEF. So F is 1, 1. Okay, E is 4, 1, and D is 1, 3. Okay. Again, we are left multiplying. We have a 90 degree counterclockwise rotation, so we're going to use this matrix. to do that. So we're going to use 0, -1, 1, 0. We're going to multiply that by our 2 by 3 matrix for here. So let's go in order DEF. So we're going to have 1, 3, 1, 1. Let's see. This is E, right? D, E, yeah, D, E, F. Now I said we're going to go in order. So 1, 3, 4, 1, and then 1, 1 is matrix F. Okay, so let's see if we can keep those in order because we're multiplying by zeros in each one, so it should be pretty easy to do without showing our work. 0 times 1 is going to be 0, so -1 times 3 is -3. 0 times 4 is 0, -1 times 1 is -1. 0 times 1 is 0, -1 times 1 is -1. Next one, 1 times 1 is 1, and then plus 0, so we have 1. 1 times 4 is 4, plus 0 is going to be 4. And 1 times 1 is 1, plus 0 times 1 is 0, so this is 1. That is our image. So let's go back and we'll graph our pre-image. So we have 1, 1, 4, 1, 1, 3. Again, best practice would be to label each of these like D, E, F, and then D prime, E prime, F prime. So please do that in your notes. Do better than I do, right? Do what I say, not what I do. -3, 1, 1, 2, 3, 1. -1, 4, -1, 1, 2, 3, 4. So let's see, this would be D prime, this is E prime, and -1, 1. -1, 1 is F prime. Okay, so again, this is a rotation. We have taken this here, that was D, E, F, and rotated it 90 degrees. So now DE, instead of being vertical, DE is horizontal in our rotation. Okay. Last but not least is dilations. Dilations. So apparently your notes aren't going to be any quicker tonight, maybe just simpler math. Okay, so dilations are the transformations where the image is reduced or enlarged, producing a similar figure. Okay, all the others were congruent, remember? Some dilations can be represented by the scalar product K times F, the matrix F, where K is the scale factor. That's important to know. While not common, a scale factor of 1 results in no change and a congruent image. And it's like, well, duh. Okay, so the dilations chart here is just telling us if K is greater than 0 but less than 1, we're going to reduce the image. If K is equal to 1, we're going to get a congruent image. And if K is greater than 1, we're going to get an enlarged image. Which you're probably thinking, duh, that makes sense. All right, so example 4. We're going to write a matrix equation representing a dilation with a scale factor of 2.5. That's the same thing as your scalar, right? You're going to write it in the front as your scalar. Multiply everything by 2.5. Then graph the pre-image and the image on the same coordinate plane. All right, this time we've got 4 points. They're kind of jumbled. So let's go ahead and just write those out in our matrix, and then we'll left multiply, or we'll put our scalar on it. Okay, so let's see, we've got P, Q, R, S. All right, so P is -2, -2. Q is 1, 2. R is 1, 1. And S is 2, 1. Okay, and so our scale factor, or our scalar, is 2.5. So we're just going to multiply this by 2.5. So each point is going to be times 2.5. All right, so 2.5 times -2 is -5. 2.5 times 1 is 2.5. 2.5 times 1 is 2.5. And 2.5 times 2 is 5. 2.5 times negative 2 is negative 5. 2.5 times 2 is 5. 2.5 times 1 is 2.5. And 2.5 times 1 is 2.5. All right, so let's graph our pre-image. Okay, so I said negative 2, negative 2. Negative 2, negative 2 is P. It's going to get really jumbled, so I'm not going to label it to start with. Q is 1, 2. R is 1, 1. S is 2, 1. So we've got this whole thing going on. Okay. Then our image is going to be negative 5, negative 5. So negative 5, negative 5. That's P prime. 2.5, 5. So 2.5, 5 is Q prime. 2.5, 2.5. So 2.5, 2.5. This is R prime. And S is 5, negative, or 5, 2.5. So 5, 2.5 is our S prime. So we're going to go, there we go. That's our image on that one. All right, we are finished up, wrapped up on that in less than 30 minutes with all 4 of those transformations. I will see you tomorrow to do some more in class.